Okay, so everybody is, of those who are still here, are alive and ready for the last two lectures.
All right, okay, I have to wait.
Ah, sorry. Yes.
And it takes me 1 minute, I don't know why.
Right. Okay. So, I think.
Well, according to the program, I should have spoken of future development of particle filters, and this morning, actually, I'm a little late. And yesterday, I didn't speak validation and evaluation of assimilation algorithm. So I'm going to speak first on this aspect of validation and evaluation of assimilation. It takes a long time. Okay, so evaluation of assimilation algorithm. So I will remind you of the context in which the blue is defined. Typical situation.
Oh, sorry.
I think I
really know.
I pretty quickly to the myself.
Yes. Yeah. Headache.
So we want to determine a state vector x, typically restricting the atmospheric flow at a given time in the format of a given numerical model, which belongs to state space S with a dimension n, and the available data are the background, typically recent forecast from the test, which is equal to the n and x less than your zeta, and an additional set of data from some observations with dimension p, y equals h of x with epsilon. Here, h is a none for the time being. Well, actually, for this presentation linear, I will not consider. And the blue, the best, the variance minimizing estimator of x is xa equal to xb plus the gain matrix times the innovation. And again, if the probability distributions are globally Gaussian, that is, if a couple zeta b epsilon is globally Gaussian, then blue achieves Bayesian estimation in the sense that the conditional probability distribution for x given xb and y is the Gaussian probability distribution with expectation xa and covariance matrix p. Yes, here I've assumed that the errors zeta b and epsilon, the background in the observation are unbiased, which amounts to assuming that we know the expectation of it. And so the determination of the blue requires, at least on the face of these equations, the a priori specification of the expectation of covariance matrix of the implicit of the error, that is the statistical moments of orders 1 and 2 of errors. The expectation is required for organizing the data in first place, and the covariance matrices are necessary, because here it is assumed that the error beta d and epsilon are uncorrelated, which is a situation we can always satisfy if we know the correlation, just like the unbiasedness. And as far the covariance matrix of beta d on one hand and epsilon on the other hand, they appear explicitly in both equations. So in order to do that, in order to be able to do that, we must know the first and second order statistical moments of the errors affecting the data, at least on the face of the equations. So this obviously raises another question. Is it possible to objectively evaluate the quality of an assimilation system? Is it possible to objectively evaluate the first and second order statistical moments of the data errors? Is it possible to objectively determine whether an assimilation system is optimal? And more generally, how to make the best of an assimilation system? So I'm going to comment on this question, to give a few partial answers, and to show a number of numerical results relative to this question. Well, the purpose of assimilation is to reconstruct as accurately as possible the state of the system. And so the only objective validation is by comparison with independent observations, that is observations that not been used in the assimilation, but more than that, but are affected with errors that are statistically independent of the errors affecting the data using the assimilation. That's rather obvious, but that's the only objective way to assess the quality of an assimilation system. It is absolutely obvious, but there's not much to say about that, but that's all. No other possibility, but only way. And secondly, the amplitude of forecast error, if an assimilation is used to start a forecast, the amplitude of forecast error, if estimated against observations that are really independent of the observation used in the assimilation, is an objective measure of the quality of the assimilation, of course. Incidentally, it is not possible to objectively check that observations are independent of other observations. This is an assumption we must make on the basis of what we know about the physics of the instruments. For instance, it is certainly reasonable to assume that the errors affecting two radio soundings made a very large distance apart with instruments made by different manufacturers are independent. That's after all that may not have yet be absolutely sure. There may be new instrument things which make the corresponding error correlated to some extent. Okay, so now, after having said that, the only objective way to evaluate objective to the quality of an assimilation system is against independent data. I come to the question of how is it possible to objectively determine the statistics of the error affecting the data. So that's background, error of Y. The only combination of the data that is a function of any error is what is obtained by eliminating the unknown epsilon, that is the innovation. So the innovation is a combination, is a function of the errors only, and it is the only, in the setting, it is the only, it contains all quantities that are in the that are function of the errors. So any objective information on the errors comes only, all the objective information of the error can come only from the innovation. Now the innovation is a combination of the observation and background error, and what we want are independent specification of, for instance, the covariance matrix of background, that is the background error, and the covariance matrix of the observational error. In fact, we'll go back to it's not, for instance, we assume that PB equals 0, then XA will be equal to XB. While if you assume that PV is 0, but R equals 0, we now get something else, and your result will depend on, of course, how these two matrices are determined, even if both are compatible with the statistics of innovation. So, innovation alone will never be sufficient to determine the quote-unquote statistics. And what can be done is just to check whether we have a system constructed of a choice of P for PV and a choice for R, and a choice for mutual correlation between the two errors, and a choice for the bias and the error. And then, from this choice, we obtain statistics of it. We can derive what the statistics of innovation should be. With the hypothesis that I mentioned, when the expectation of innovation must be 0, and the covariance of innovation must be H, PV, HT plus R. Once I've chosen PV, R, I decide the data are unbiased. I can deduce that the statistics of innovation must be what I've just assumed. If epsilon and h of zeta b are supposed to be unbiased, of course, d is unbiased, b has expectation 0, and actually, yes. This matrix which appears here is, within the brackets, is the covariance matrix of innovation. So, with the hypothesis I've made, the statistics of innovation must be expectation of D equals 0, covariance of D equals HPV plus HT plus R. So what I can do at least is to check statistically every day of a new set of the new innovation, do the statistics of innovation, and check whether we're consistent with that. At least I can check to some degree the internal consistency of the system. Is the statistics of innovation consistent with the hypothesis I put in the first place in my system? This I can do. So I consider a scheme which may not be optimal. In fact, one of the questions I would answer is whether the system is optimal or not. One question of the form XA equal XB plus the matrix K times the innovation. But with the K I've chosen on the basis of a choice for R, PV, etc. But which I know may not be optimal. One of the questions being precisely determine whether the system is optimal. This scheme is actually rather natural. Schemes of that form, linear schemes of that form, are those which are the property that if the data happens to be perfect, then the assumed XA is perfect too, which of course is the desirable feature. The assimilation process does not degrade the information contained in the data. And you see easily that the scheme possesses this desirable property, if and only if it is of this form with any K. So I consider a scheme of this form. Question?
Yes.
Yes.
What do you mean by the data perfect?
If the data happens to be equal to 0, if epsilon and zeta b happen, but for some extraordinary stroke of luck, to be 0. It will never be, but, but this condition is that the assimilation does not degrade the data. It does not degrade exact data, at least. see that it will be of this form. And of course, variational assimilation and Kalman filter are of this. Now, one quantity I can consider is not the innovation, but once I have done the analysis, the difference between the data and the analysis. That is xb minus xa, which will be k times the innovation, for this formula, minus the innovation, and y minus hxa. That is the difference between the observation and what the analysis gives of the observation. I can look at that. It's not at least, not at all a measure of the quality of the assimilation, but I can look at it. And interesting fact, is that this quantity, delta, is in one-to-one correspondence with innovation. If I know the innovation, I know this. If I know this, I can eliminate the term HKD by just adding here, multiplying here by H, and making the subtraction, and what remains is E. So there is a one-to-one correspondence between the innovation on the one hand, and the data, and the difference between the data and the analysis. When I say data, this includes the background. This one-to-one correspondence is not, D and delta don't have the same vector dimension. D has dimension P, with the notation that defines, and delta, which in the space of all the data, has dimension n from here and p from here. So delta has dimension much larger than this means that there are many components in delta that are redundant, that are functions, but many linear combinations of delta which are necessarily zero. But it does not change the fact that there is a one-to-one correspondence between the two. For given k, for a given matrix k, there is no whether it is optimal or not, there is a one-to-one correspondence between the two. So if I want to do statistics of innovation, I can do as well do statistics on the data minus analysis difference. In terms of statistical significance, it will be the same. So it's essentially a matter of convenience. I can do the statistics on either one. So it is exactly equivalent to compute statistics on either innovation or the data minus analysis difference. So in case some of you thought, I see faces, this again my horrible scan figure, but it is not illustrate what it is. This I said is the background. And here, observations have been plotted. For instance, 957 surface pressure observations, which almost coincide with 960 hectopascal pressure in the background. So there is a difference of 3 hectopascal, which is one component of innovation. There is also another surface pressure measurement of 990 hectopascals here, which is at the position which in the background is less than 990. So the difference here, again, is one component of innovation. And that's the analysis. Terms, contour lines and the vectors. Here, the contour line and the vector are the background. And observation that is plotted on top of it. The differences between those two make up the innovation. Here, this is the analysis. And again, I can compute the difference between the analysis and the observations. For instance, the 957 hectopascal surface pressure observation, sea level observation, sea level pressure observation, as a location of something now 958. So the difference, which is one component of the data minus analysis difference. Same here, 990 observation in the position to be 990.5 hectopascal. So that's the component of the data minus analysis difference. So if we want to accumulate statistics, we can accumulate statistics either on the innovation or on the data minus analysis difference. For given k, varies. Well, for given k, the same. There is a one-to-one correspondence. Okay. First of all, now I do this. For a perfectly consistent system, a system that uses the exact error statistics, the innovation must be unbiased, and the data minus analysis difference must be unbiased. So, if I find a systematic bias in either the innovation or the data minus analysis difference, that is the signature of an inappropriately taken into account bias in either the background of the observation, or both. Either the bias in innovation or a bias in the data minus analysis difference. This is a significant statistically significant bias that is a sign of an inappropriately taken into account, of a bias somewhere hasn't been properly taken into account. That's why they're obvious, but I mentioned it. But of course, this bias doesn't tell me where the presence of such bias doesn't mean where a bias has been inappropriately taken into account. It doesn't tell whether it is in innovation, whether it is in the background, or in the observation, or in both. If I want to do more, I have to make a hypothesis. I look also at the difference xb minus xp, and take, assuming it is by bias, take the covariance matrix of that. It is equal to PB minus PA, where PB is the covariance matrix of the background, and PA is the covariance matrix of the non-statistically. This, in the sense, is Pythagorean theorem. And this is positive. The diagonal terms are positive. Same thing for the difference y minus Sxa, y minus Sxa transpose expectation. It is R minus the positive term. Which means that in perfectly consistent analysis, this perfectly consistent analysis fits the data to within their own accuracy. If I specify a 1 hectopascal error on surface pressure observations, and the analysis statistically fits that observations with, let us say, an accuracy isn't the word, but the misfit is 2 hectopascals, larger than what I have specified. This means there is an inconsistency somewhere. The fit of the analysis to the observation, to the data, background, and observation must be within the accuracy specified in the data. But if I find such a misfit, it doesn't tell me where the inconsistency is. It might be a way of specifying the errors in the data, but it might be elsewhere. And I stress one point here. If I am, for instance, one observation for one quantity, the analysis will tell me that the analyzed value is the observed quantity. So the fit of an analysis to that particular piece of data will be exact. Now if I add additional data, other observation of the same quantity, or observations of other quantities which are related in some way to what I want to achieve, then the fit of the analysis to that particular piece of data will not be 0, will become greater than 0. And the more information I use, the larger the fit will be. And asymptotically, the fit of the analysis to that particular piece of data must be equal to the error statistically, to the error in that particular piece of data. So that when I improve an estimation system by adding new observations, and if I do the things correctly, the fit of analysis to one particular piece of data will become larger and larger to eventually be equal to the errors on that particular piece of data. So that an increase of the data minus analysis difference by no means signifies that something has degraded in the analysis. It might very well be on the opposite, a sign that the analysis has improved. Because as long as the error, the fit of the data to the analysis remains less than the assumed errors in the data, that's consistent with what we can expect. This also shows that, of course, the fit of the data to the analysis is by no means a measure of the quality of analysis. Actually, the fit of the analysis to any particular piece of data can be made arbitrarily small by simply assuming that the error in the data is small enough. So it's not. Okay. So now, other questions about that? A human inconsistency has been found between a prior assumed and posterior observed statistics of indirection or the data analysis difference. I found an inconsistency. For instance, the fit of the analysis to the data, the fit of the analysis to the surface pressure observations assumed to have been observed with a 1 hectopascal standard error turns out to for 1.5 hectopascal. So it's large. Incidentally, now I think most systems, at least in large meteorological centers like ECM and ECMWF, most systems now satisfy the condition that the fit of data to analysis is within the uncertainty of the analysis. Specified within the a priori specified uncertainty in the data. It has not always been like that. There was a time, I know examples of a 100 factor between it was an example of a weak constraint of simulation in which the fit of fields to the model equation was 100 larger than what 100 times larger than what was implied by the corresponding Q matrix. So this is proof of a major inconsistency in the system. So assume that an inconsistency has been found. What can I do in terms of purely objective analysis? What can I do? Or equivalently, which bounds does the knowledge of a statistic of innovation put on the error statistics with knowledge is required to do? I found that something is inconsistent. So this must restrict, must be bounds on what PB and R and their mutual correlation and the biases can. So what are these bounds? Can anyone suggest an answer to the question? To answer that question, I now lump together the background and the observation. I don't make the explicit distinction between the two anymore. And I consider a problem in which I have an unknown x, a set of a vector of data z of the form gamma x z equal gamma x is zeta. Gamma is a known n matrix, n is the total dimension, and zeta is an unknown error. So, in case of the data in format background observation with observation operator H, that means that gamma consists of the matrix, it consists of the unity matrix with order n on the top and H on the bottom. And zeta consists of zeta the NSR. And now I look at what can be thought of a new estimation problem. I look for an estimate of a form alpha, where alpha is a vector in field space, times AZ, where Z is a matrix to be defined, representing an operator from a global data vector into the state vector. And subject to two conditions. Invariance in the sense of origin in state space. That if I decide to express the temperature in Kelvin or in Celsius, the result will be the same, which is a desirable property. And second property, once I impose this, then I can have an estimate of a quadratic estimation error, xa minus x, a minimum for any component in x. Look, solve this problem. And I obtain, but the solution to that is xa equals z minus the expectation of the error on z times a matrix, which is here, which actually is the left inverse of gamma. That's, I think that's the third name is called the OR matrix. And have an associated covariance matrix for the estimation error, which is equal to gamma transpose S minus 1 gamma minus 1, and in this expression, mu is the expectation in the error, and S is the covariance matrix of mu. So this again, at least on the face of it, requires the explicit knowledge of both the expectation of data and the covariance matrix of this. Well, this is unambiguously defined if the rank n of n is equal to n. That is, if two different states produce two different states produce two different gamma x. There is no non-zero x, so that gamma x equals 0. This is the determinacy condition, and okay, it makes sense only under this condition. This is invariant in any invertible linear chain of coordinates, either in data or state space. Right? And again, if zeta is Gaussian, then this achieves Bayesian estimation in the sense that the conditional probability of x given z is the Gaussian probability distribution with expectation xa and covariance matrix p. So I won't be surprised, I think, if I tell you that this is just another form of the blue. Just what the blue becomes when one does not make explicitly the difference between the background on the one hand and additional data on the other hand and the other, and one puts everything together without making the difference. But so if, I said, if the deterministic condition is verified, it is always possible to decompose the data vector z into a first estimate of x plus additional information, and then you can find the same formula as before. But that new approach does not require an explicit distinction in the data between the background and additional observation. Fundamentally, it is the same. And now the variational problem with solution is xa, is simply the problem of minimizing a scalar function j of psi, where psi belongs to the space, which is equal to the squared of the difference gamma psi minus z minus mu. Here I explicitly keep the bias in the expression, because I need it later, weighted by inverse covariance matrix of the errors on the global data vector z. And this, as I told you yesterday, define on data space scalar product, a proper scalar product, which is the Mahalanobis norm associated with the covariance matrix S. So what does it mean to minimize that? I'm looking for the point size belonging to the image space of gamma, which is closest in the sense of a Malebis norm of a point z by n minus p. So that's a very simple explanation. I look in subspace to the point which is closest according to a certain norm to some point which can be anywhere in the space. The solution is that the space I look in the subspace is the orthogonal projection, in the sense of the particular scalar product I'm using, of a point onto the subspace. So I move on that. This is the image space gamma S. This is the whole data space. I take the data vector, I subtract mu, I subtract the bias, I project that onto the image space according to the Mahalanobis scalar product associated with S. So I get gamma of its A, and then I take the inverse of that for gamma, which is uniquely defined because gamma has full rank. So once I have a point in the image space of gamma, its inverse in the original state space is uniquely defined. Okay. Does everybody follow, or does it become way too abstract? And it means something that behind all what's spoken about, variational assimilation, Kalman filter, Kalman smoother, all that, in a sense, there is only an orthogonal projection, as long as it is linear. So that's why some mathematicians say, well, the problem at that way is simply devoid of any interest. You only do orthogonal projection, so what is the interest of all? Though if it is useful for you, but it's not interesting for me. So what you do is unbias the data vector, project it orthogonally onto a space gamma according to the Mahalanobis metric, and take the inverse of the projection for gamma. Inverse is unambiguously defined because gamma is a front. When you do Kalman filter, variational assimilation, whether it is strong constraint or weak constraint of variational assimilation, whether you use the primal or dual algorithms I mentioned yesterday, you do, in a sense, you do only that. But then, it has significance for the question I asked. I decompose, well, do I really need that? This, except from well, I have mu. Mu as a component along that direction, and mu as a component along the direction parallel to gamma. The component along this direction, orthogonal, S orthogonal to gamma is irrelevant for the analysis, because when I shift, because that component is, doesn't have no impact, when I subtract mu from that direction. It has no impact on what the projection here. So the component of mu that is S orthogonal to gamma S plays no role in the assimilation. Yes.
Oliver, I think it's a bit too abstract.
It's a bit abstract.
I mean, it would be nice if, because we're examining some sort of construct, without,
Yes.
if you get idea what is supposed to be the output of this procedure before going through it. We want to estimate the bias of observation or something.
No, I don't want to, at this stage, I don't want to estimate the bias.
It's just,
I'm just doing an analysis,
just investigating this.
in description of what we do.
Okay.
I'm just doing a description of what we do. And I said that the component of a bias, that is S orthogonal to gamma of S, or the same S, the same, this one. So when I say S orthogonal to gamma of S, it's very ambiguous. If the component of a bias, which is S orthogonal to the image space, doesn't play any role in the analysis, because it doesn't change gamma S. Similarly, the component of the covariance matrix on VR zeta, yes, that covariance matrix separates red covariance matrix. Red covariance matrix, S. Once I use as coordinates projection along the image space and the projection orthogonal to the image space, becomes something like that. Zeros, because precisely that matrix represents S, and I consider S a orthogonality. This means that S reduces to two components: a component that is orthogonal to the image space, and a component which is along the image space. And only the component which is along the image space matters. Because when I do the projection, there is a certainty on Z defined by the covariance matrix. I project here, so uncertainty projected into that, and it is only the uncertainty projected into that which matters for the accuracy and this. Okay, that's too abstract. So you papel from my face. All right, sorry for that. But the consequence of that is that the components of the error of precisely the components of the statistics of this error statistics that are orthogonal to the image space are irrelevant for the analysis. I can modify them without modifying the analysis. Now the component that is orthogonal to the image space is precisely the data minus analysis difference. No, I take the data, mu, I took the analysis in the format of a theta, can I say? So this is precisely the data analysis difference. So the data analysis minus analysis difference, which is in one-to-one correspondent with innovation, plays no role in the analysis. So when I make statistics on that, I make statistics on quantities which are actually irrelevant for the analysis. I make statistics over the residual, which actually is what I rejected in the first place. Because the first thing one does in doing the analysis is rejecting those components of the system, those components of the data that are orthogonal to the image space. So the consequence is that the knowledge of the statistic of innovation or equivalently of the data minus analysis difference brings no bound of any kind on what the statistics I want and need should be. Okay. The expectation for that. No, I'm not going to write the action. Consequence. The DMA difference is in effect projected by the assimilation. Its expectation and covariance are relevant for assimilation. Consequence. Any assimilation scheme, that is, a prior subtracted variance and gain matrix at an analysis scheme is defined by the bias as subtract in first place and the gain matrix. Any analysis scheme is compatible with any observed statistics of either the DMA difference or the innovation. So the consequence is that I implicitly said that statistical consistency between the a priori specified and the observed statistics of innovation was not a sufficient condition for optimality of the system. It is not even a necessary condition. You can be off in the consistency checks and still be optimal. It's neither a necessary nor sufficient condition. Well, for those who find that too abstract, find that I have specific examples here, but I will not comment on it because I want to say other things explicit example. One piece of data to be, one parameter to be estimated, and two pieces of data. X1 equals Z1 equals X plus data 1 plus 2 equals X plus data 2. Which shows that can be optimal with any statistics of the linear statistics of innovation of the data and anything different. Well, the explanation, maybe that will be effective or not. It is not necessary to know, contrary to what the formula, the standard formula of blue, seem to imply. It is not necessary to know explicitly the complete expectation mu and the complete covariance matrix S in order to perform the assimilation. But it is not necessary. It is not necessary to know everything. It is necessary only to know the projection of mu and S onto the subspace, the image subspace of gamma. What is orthogonal is irrelevant. As for the substrate that is S orthogonal to gamma S, it's sufficient to know what it is, but it is not necessary to know the projection of mu and S onto it. A number of degrees of freedom are therefore useless for the assimilation. That's the crux of the argument. A number of degrees of freedom is useless. You don't need to specify entirely PA, PV, and the biases. The parameters determined by the statistics of D are equal in number to the useless degrees of freedom, to which any inconsistency between a priori and a posteriori statistics of innovation can always mathematically be attributed. So the property of strict mathematics, the problem is that the complete determination, complete knowledge of the bias and the covariance matrix of the errors is not necessary to perform the analysis, and there are useless parameters, but it is on the useless parameters that the statistics of innovation are actually computed. So if there is inconsistency, you can say, oh well, the inconsistency comes from the fact that I've misspecified parameters which anyway are useless for the assimilation. From a mathematical point of view, we can say that. So what would change the analysis? What matters? What matters, of course, if you change the statistics of the errors, usually you will change the matrix S in a way which modifies what the orthogonal space subspace to the image space is. And changing for orthogonality, changing the analysis, because instead of projecting like this, you project like that, and that changes the analysis. And when you do a modification on the variance of the assumed covariance of I don't know which component in the background, you may very well change in the orthogonality. And in general, you will actually, although it might be very difficult to check whether well, do. If you change the analysis, it's a problem. You change the orthogonality, because if you didn't change the orthogonality, you wouldn't change the analysis. But you have to run the analysis in order to check that. Now, yes.
And so some degrees of freedom will sometimes be useless, but at other times they will become useful again.
Yes, if absolutely. Yes, if something changes, if you add new observations, they might become useful again. Yes. I mean, what I described is purely mathematical, but it means that there cannot be a foolproof numerical algorithm which, starting from the inconsistency between the a priori specified and observed statistical innovation, brings an improvement in assimilation. There cannot be a foolproof numerical algorithm which does that. This is what I say. The general, you must introduce hypothesis, physical hypothesis in such an algorithm. Okay. It may be that resolving the inconsistency in that way requires conditions that are independently known to be very unlikely, if not simply impossible. I'll give an example from that example. And this, the results, which is purely mathematical, means that the specification of the error statistic required by the assimilation must always be based, at least the last result, on external hypothesis, that is, hypothesis that cannot be validated on the basis of innovation alone. As long as you are in the world of data and model, what will not be sufficient to determine the required statistics. Now, external knowledge is always exists more or less. For instance, if, as it happens, people observe, this has happened in the situation I'm going to describe, people observe that the observations performed on a given meteorological station lead statistically to innovation that are distinctly different to the properties and innovation performed, the associated with observations performed in another station and in other stations, in other similar stations. And that particular station produces innovation which is statistically different. So, according to what I said, it would be impossible to determine when the inconsistency comes from. Inconsistency comes from. But if inconsistency persists, and in particular is observed in different models, well, according to what I said, it is not possible to tell whether an inconsistency comes from the observation or comes from the background. But if, with the same background in neighboring station, there is not that type of inconsistency, and the same thing is observed actually with different models and different sets of innovation, then it becomes absolutely obvious that the inconsistency comes from the fact that the observations are not processed properly in that particular station. And this has appeared, and I can tell you, I know the case of the CMWF, but there has been a number of meteorological stations around the world to which ECMWF has been able to say, well, I'm sorry, but the statistics performed on your observation show that there is something wrong with your observations. We ask you to check that. Of course, in such a situation, it is obvious that the inconsistency comes from the fact that data are made or processed in that particular station. But when we come to this conclusion, we use information about the observing system, which is not contained in the assimilation algorithm as such, because we know more about the observing system than what is simply included in the assimilation code by itself. So this shows that it is very important, I think, to, so to speak, rank the hypotheses which are behind an assimilation system. Hypotheses that are unlikely to ever be questioned. For instance, errors and observations performed along distance apart by radiation by different manufacturers are uncorrelated. Likely to be questioned. Unlikely to be questioned. But sound reasonable, but they certainly be questioned. Observation and background errors are uncorrelated. Well, the background comes from the past, the observation and the observation, but it's uncorrelated. Well, satellite observations have been performed and be used for previous analysis, have influenced the background and have some impact on what the background error is. And the same satellite performs observations which are used in the new set of observations. So then I did correlation with the background. And hypotheses which are introduced but which are unlikely questionable, for instance, that model errors are negligible, which is an hypothesis that is made in strong constraint variational assimilation, and then what hypothesis is made out of convenience. Don't sleep. Not many people in the fields would bet much on the hypothesis that the errors are negligible. So ideally, what we might be interested is to define a minimum set of hypotheses so that all remaining undetermined error statistics can be objectively determined from observed statistics and emulation. We make enough hypotheses so that the determination of the remaining statistics is a well-posed problem. But of course, that's very difficult. and all the more difficult, but the observation system evolves permanently, and new observation become available, so that's parametric constantly, and that's constantly new problem along the lines. New question. Okay, we remain a few minutes. Our questions on this aspect? I hope I've not confused you too much. We look at the analytic function at the minimum. And we do the algebra. So what's the complete objective function? No, it's a complete vector Z, which normally separates into two terms, a G day term and a G O term. Lump everything together. Well, I look at the objective function as the minimum, the value xa of the argument. So here I get gamma xa minus z, that is precisely the data minus an RC difference. That, and I found that it is equal to 1/2 d transpose expectation covariance of d minus 1 d. Well, this is the assumed covariance matrix for the innovation, HPD HT plus R. Indeed. So that's a very good, very clear example, but the statistics, actually this is deterministic. This is true. Yes, this is true for any realization of a system. This is true for any realization of an analysis. The data minus analysis difference, this is a function of the data minus analysis difference, is a function of innovation. It is one particular instance of the general statement I made that there is a one-to-one correspondence between the data minus analysis difference and the innovation. Now I take the statistics of that. And if the D that is here has really covariance matrix defined here, the value, expected value of the objective function of the minimum is P over 2, where P is the dimension of this. So the objective function statistically has a well-defined value at its minimum. And in practice, if P is large, a few realizations are sufficient for determining the expectation of J min. In particular, if in addition the errors are Gaussian, then variance of J min equals to P over 2. So variance, P over 2, not P squared, P over 2. The variance is P over 2. So that the square root, the standard deviation, the square root of P, which is very small in comparison with P, if P is large. So that the distribution is very peaked. So that it's easy to determine the expectation of the J min with only a few realizations of the system. This is often called the chi-square criterion, in which actually some fields of people in estimation, this is a well-known theory of result of estimation field, even called this quantity the chi-square. You may know that the chi-square probability distribution over the P is the distribution of the sum of the squares of P independent Gaussian observation, each with expectation 0 and with variance 1. And chi-square over the P, in assembly terms, equals summation from I1 to P of Gaussian distribution with expectation 1 and variance, expectation 0 and variance 1. No, sorry, that. Yes, it is that. The sum of the squares of a Gaussian. And if the errors are Gaussian, you find that the J min is of this form. So J min follows a chi-square distribution if the errors are Gaussian. But this result remains true even if the errors are not Gaussian. So that's the reason why I would tend to avoid to call that the chi-square criterion, which strictly speaking is justified only for Gaussian probability. Anyway, that can be done. That check can be done. you can verify whether the minimum of the objective function is statistically equal to P over 2. That's very easy to do. You just look at the minimum of your objective function. And I did that. There we go, the system of ECMWF, and I found that the ratio which would have been equal to 1 was typically a value 0.4. And this means that the real innovation is significantly larger than implied by PB and R. Because if I come to the previous picture, I found that it was the ratio that was the peak, so that means that yes, it was one. It means when you do that, when you do the expectation, if D is very much smaller than implied by that, you obtain, of course, a quantity which is smaller than P over 2. And the opposite, D is significantly larger than what is implied by what was specified in the system. And I found that with when I made an estimation without satellite observation, that I had a ratio which was much closer to 1, which seemed that there was a kind of global consistency for non-satellite observation, but not for satellite observation. The situation that's improved in that, but not totally. I mean, I think this is still a very useful criterion. No, there is not much time left. I simply say that this criterion of consistency, the so-called chi-square criterion, can be extended to any subset of data. For any subset of data, you find that in a sense, I consider a subset of data associated with a covariance matrix and error covariance associated with an observation operator HK and covariance error matrix and error covariance matrix XK, and you find that yes, the quantity, the trace of the matrix SK minus 1/2 HK P HK transpose SK minus 1/2. HK minus 1/2 is taken par the top of this is not uniquely defined as square root of the matrix. In that case, it is defined as we said by diagonalizing the covariance matrix with a new unitary matrix and then taking the square root of the diagonal matrix. And you find that this quantity is a measure of the informative content of a contribution that a particular set of data, it may include the background, part of the background, but a particular set of data brings to overall accuracy of assimilation. The quantity is a measure of relative contribution of subset of data yk to overall accuracy of assimilation. It is invariant in linear change of coordinate in data space, so that it is valid for any subset of data. It is this quantity that Clive Rogers, in his book on inversion of satellite observations, calls degrees of freedom for signal or degrees of freedom for noise, depending on whether the considered subset belongs to observation of background. This, you mentioned that. I must say that I fully agree with this expression, which seemed to imply that observations is more for signal and background more for noise, which of course indicates both information, both sets of data containing both useful information and noise. And can separate signal and noise as being observation on one hand and background on the other, or the opposite. Anyway, it's possible to measure for a given system, that is assuming that the specified statistics introduced of the system are correct, the amount of information contained in each subset of data. Here this has been done for various types of observations, and there is more information in some data than in others. I must say that the information content is to a large extent linked to the number of individual observations. And that this information content is actually, in a simple case, only a kind of normalized measure of the weights given by the assimilation to a particular subset of data. It's just normalized, taking into account that there are different figures you need, and it's just a measure of that. What might be more interesting is to measure that information content per individual scalar observation. And in that case, that was done on the system of French Meteorological Service of Météo France, we found a particular set of observations which brought most information per individual scalar observation was the humidity measured by a radio source. It was a consequence which we did not expect, but with what we assumed for the statistics of error, it was the measurements of the radio sound measurements of humidity which brought most information per unit scalar measurement. Okay, I think it's time. I'll stop. I could everything. This notion, yes, of course. There is a relationship, just as the objective function at its minimum is equal to pi, to p over 2. Statistically, must be equal statistically. I can look at any term in the objective function, which is the sum of terms. I can look at any term in the objective function, each term being associated with a subset of data. And I find that the minimum, at the minimum of the objective function, the expectation of that term of a given term of minimum is 1/2 nk. Nk is the dimension, the vector dimension of a subset of data, minus the same trace of which I said it measures the relative contribution of that subset of the data to overall accuracy of the system. And that can be checked objectively. Two terms can be totally independent. This typically are computed for a Monte Carlo method. Two terms can be computed independently. And then you can adjust the parameter of the simulation to make these two quantities equal. But again, which parameter of the simulation to be adjusted? There are more degrees of freedom at the disposal than data to fit. So there is the problem of adjusting is not fully determined. You have to make a hypothesis. And again, the arrangement of hypothesis you can make only on the basis of knowledge of a system beyond just the model and the observations. Again, you never avoid the need for hypothesis which cannot be objectively verified. Okay, well, I'll stop here for this part. I can make it.
Thank you. Questions?
I hope I'm not being too abstract.
Yes.
Okay. Yes.
So when you found that there is inconsistency in simulating satellite observations,
Yes.
what did you do about it?
Well, what did you do about it? Well, in the case of this work we did with yes, it was the research consultant. We found and what we did was to re-establish the consistency by multiplying each covariance SK by a coefficient alpha. That was mounted to assume that the misspecification was the amplitude, so to speak, of the variances, not in the covariance, knowing the fact that different subsets of data were uncorrelated.
So you tuned the observational error.
Okay, you did the observation. Yeah. And this led to a small improvement in the quality of the photos. A small, but not a one which can really goes to part. Just tuned the observation error. Of course, what I've said here is mostly a kind of partial, as I said, there's a partial answer to the questions I put at the beginning, and the answer is we will never avoid the need for hypothesis, which require knowledge of the system beyond what happens just in the world of observation, numerical value, and model. That's rather natural in the sense that there cannot be a foolproof algorithm, a foolproof numerical algorithm, which can improve assimilation just by analyzing the inconsistencies. Inconsistencies must interpret inconsistencies, require physical knowledge, physical in a very broad sense, real knowledge of the system, including how the observing system is organized and is managed by people. For example, I said of that particular meteorological station that has happened several times, which were identified as not processing very clear observation, and to do with the knowledge of how meteorology works from the point of view of people who do it, people who do it with information. Yes.
So those hypotheses go into the operators H and M, is that?
Yes, well, it goes. It goes.
Well, what I'm saying is, obviously, you're saying that you can't. It's not just a completely defined model. You have to add hypotheses about the physical nature of the atmosphere or whatever. Yeah.
Well, in a sense, people, of course, always been doing that. I mean, some people, when I say that, comment, well, you're saying thing by which actually we've always known. We've known that we need a good knowledge of the whole world of the atmosphere and the world of meteorology for doing that. We always knew we could not rely on blind numerical algorithms.
But what I'm asking is, where does that knowledge finish up in these algorithms?
Well, it finishes up in various forms. I mean, people constantly look at the consistency. I said now it's absolutely standard to look at the misfit between data and analysis, and to look at whether the misfit is statistically smaller, the difference is statistically smaller than the assumed error in the data. And even when it can be something found, now people try to find where it comes from. Of course, if an inconsistency, it may not be obvious at all. I mean, the inconsistency may really be somewhere else than where we observe it. Not obvious at all. Again, there are more degrees of freedom you can play with in order to remove the inconsistency than parameters which show the very inconsistency. That's absolutely general. You have more buttons on which you can control than quantitative data. Yes.
Within the information content, you mentioned the relative humidity.
What do you say?
The case of humidity, yes. I mean, you would expect that relative humidity has a low information content, isn't it?
Yes, well, we were surprised when we saw that.
What is the reason?
I must say I have not particularly looked. The reason lies in what was specified for errors, for statistics of error, both biases and covariances. So maybe it is in the fact that the statistics on, maybe it is, but the variance, error variance on the statistics of the error was taken to be too small, because if it is too small, well, informative can no or too large. I have to check, because if you look at this formula, if you change SK, if you increase SK, yes, if you increase SK, you basically decrease this term, so it makes them larger. So maybe it was simply that the assumed error on the humidity was actually assumed to be smaller than it was really. Of course, this will give a larger weight to humidity, and they say, but you trust But the system trusts humidity maybe more than nature.
So the hypothesis you mentioned earlier on remain always subjective.
There is always some subjective hypothesis in the end. Subjective. When I say subjective, it doesn't mean arbitrary or erroneous, of course. But not impossible to check objectively on the basis in the world of data of model. You see what I mean?
But still based on the chi-square, which is, again, subjective.
Not necessarily, well, the chi-square criterion, or this criterion, which is the generalization of the so-called criterion, is objective. This is a numerical objective criterion. And if you find that there is an inconsistency, but still these two terms are not equal, then it means that there is an inconsistency somewhere. But what you've specified is not the real statistics. What you've specified of statistics is not the real statistics. But one of my points is that even so, it might be that inconsistency lie in parameters, in both parameters, but as useless for assimilation. So that it does not mean that the analysis, if you find an inconsistency, it does not necessarily mean your analysis can be improved. Because the inconsistency might lie, or it may be rather unlikely, but mathematically it might lie in parameters, which in both parameters, but precisely are useless for the assimilation.
If there's no further question, then we have a break.
Okay.